Hello, this is AP Calculus Section 1.7 notes. Today we're going to be doing something kind of different than what we've been doing lately, and this is going to be heavily involving our graphing calculators. So the first thing I want you to do right now is pull that out because we're going to be using it the entire time. What we're going to be doing today is talking about mathematical models and trying to find a mathematical model like a function or an equation that we can use to model a set of data. And a mathematical model, by definition, is a mathematical description. Usually it's a function or an equation of a real-world situation. And the purpose of the model is to better understand the situation and also to allow us to make predictions about future behavior. So we're going to use our graphing calculator. It's going to do most of the work for us, but there is a bit of a learning curve as far as how to use the calculator to help us with this process. Okay, so we're going to then, once we have the calculator help us create a model, we're going to use those models to either interpolate, which means to estimate values that are between observed data, or to extrapolate, which means to estimate values that are outside our region of observation. Okay, so here are the steps, and you're going to be referring to these every single time you do one of these problems until you get used to the process. But I promise you do enough of them and you will get used to the process. It looks a lot more complicated than it actually is. So to do regression or curve fitting on a graphing calculator, okay, the first thing we're going to do, and we're going to do this with example number 1 or problem number 1 on page 82 of your textbook. Okay, so they've given us this table right here. And this table represents average income of people and the ulcer rate associated with the incomes. Okay, and when we say we're talking about stomach ulcers here, right? So it kind of makes sense that people that make less money are probably more financially stressed, more worried about money, and so those ulcer rates are higher. And as the annual income increases, the ulcer rate seems to be dropping. But right now, all we have is this table of data, and we don't really have any information about what type of model this might be, and so we can't really make any guesses about future behavior without first figuring that out. So the first thing that we're going to do, and again, I'm just following the step-by-step curve fitting process on the page in your notes here. So step number 1, we're going to go to our graphing calculators, and we're going to go to Stat, Edit, number 1, okay? So your stat key is right here, okay? So stat, and then edit, so we're gonna click edit, and right here is your table, okay? Now you may or may not have anything in here, but you can just go and you can click here, you can use your arrows to move around in the table, and if you have something in there that you want out, you can just go to L1, hit clear, and hit enter like I did. Arrow over to L2, go arrow up. Actually highlight L2, hit clear, and then enter, and it just cleans out what was there. Okay, so now you can have some empty columns if you had stuff there. And you literally just have to type the data in. So this does take a couple of minutes, but it's not a big deal. So 4,000, 6,000, 8,000, oops, 12,000, 16,000, 20,000, 30,000, 45,000, and 60,000. All right, so I have my income in there. Now I'm going to go to L2, and I'm going to put my ulcer rates in there. 14.1, 13.0, 13.4, 12.5, 12.0, 12.4, 10.5, 9.4, and 8.2. Okay, so now that we've entered our table into columns L1 and L2, Step 2, we are going to go second level, and then we're going to go stat plot, which is up here above the y equals. So you hit your second level function, and then you hit the y equals, and it says stat plots, okay? And we want to turn plot number 1 on. So we're going to hit enter, okay? And then we're going to arrow over here. Whoops, we're going to arrow over to on, make sure that on is flashing, and we're going to hit enter. So it's going to change the plot to on. And our stat plot is going to be blue. That doesn't matter right now, but if you have multiple stat plots going, the one that we're working on for the L1, L2 table is going to be blue. Now, if you look down here, you can see that it says your X values are going to come from your L1 and your Y values are going to come from L2, because right now those are the only tables that we have data in. If we had other tables filled on that page, then you'd have more options here in this section, but it's going to default to what you have, which is L1 and L2 right now. Okay, and this just shows what the stat plot's going to look like. It's just going to plot these little squares. If you don't like that, arrow down, and it'll plot plus signs. It'll plot like square dots. I'm actually going to change mine to the square dots, okay? You can leave it at the open squares if you'd like, but I prefer the square dots. All right, so now we have done step 2. So this is going to turn my data points into a scatter plot, okay? And now I want to take a look, okay? And there's a special zoom key here for our stats, okay, which is the zoom stat key, which is number 9. So let's go the zoom 9, and it should automatically create a perfect window for us that fits our data. So that is what you should have on your screen, the same thing that I have on my screen. Okay, that's a picture of our scatter plot of our data here. All right, so now we get to play with fitting a curve to the data. So we're going to go stat, and then we're going to go over right here to calculate. So you're going to arrow over to calculate. And then we have all kinds of options down here for what we want to calculate. These are the different types of regression. So you could do linear, quadratic, cubic, quartic. So think about what these things typically look like, right? Linear looks like a straight line. Quadratic looks like a parabola. Cubic looks like a standing snake. Quartic looks like a parabola, but it has a little wiggle jiggle in the middle. So on and so forth. And there are actually more below here. If you arrow down, you will see that there are other options. There's exponential, there's power, there's log, there's sinusoidal. So there are other options as well. Most of those we're not going to look at. We're going to kind of stick to the basics here. Linear, quadratic, cubic, quartic. Those are going to be the main ones that we're going to try to take a look at. All right, so we're going to select one of the models, and we're going to try them. We're going to do, let's take a look quick first at our graph again. And you see this shape, right? So it's possible that a straight line could model this data. It's also possible there's some curvature there, that this could be exponential, right? Exponential decay. It's possible this could be half of a parabola, which would be quadratic, or half of a quartic model. This could also be part of a cubic, and we just can't see what's going on outside of our data set. I don't know that that would be the best model, but it's always a possibility. Okay, so we're going to look at them all, and we're going to go through this process multiple times and then try to figure out which one we think is the best one. So let's start with linear regression. All right, so again, we're going to go to that stat, arrow over to calculate, and let's start with a linear regression. Okay, AX plus B. So we hit enter. All right, now it's going to ask us some questions. And most of these you don't have to do anything with because the information is already where it needs to be, right? So it's going to ask you to choose your X list as L1 and your Y list as L2. Frequency list we're going to leave blank. All right, now store the reg EQ. This means when the calculator creates a model for you, would you like the calculator to store it somewhere for you? Yes, we definitely would. That would be extremely helpful. Okay, so we're going to tell it to store the model that it comes up with in our like Y1, Y2, Y3 equals, where we usually do our graphing. Okay, so to get to that, you're going to hit the alpha key, which is right here, alpha, and then you're going to click on your F4. So alpha F4, which is above your trace key right here. So hit alpha trace. And since it's the first one we're doing, we're going to choose Y1. Okay, so it's already highlighted. We're going to hit enter. All right, so we just told the calculator that when it comes up with a linear model for our data, we want it to put the equation that it creates in the Y1 equals. All right, so then we're going to arrow down to calculate, and we hit enter. There is the model, the linear model that our calculator came up with for us. Okay, so y equals ax plus b, where a is like our slope. So this number right here is our slope, very tiny. And this number is our y-intercept. Okay, so we can go ahead and we can write that model down. Or if we want to, we can go over to y equals, and we'll see that the calculator put it in there for us. Okay, but we're going to want to write it on our paper at some point. So on my paper, I am going to write that. And actually, we're doing here part C. We'll come back and we'll look at parts A and B later. We're going to do part C, okay, which was linear regression. And linear regression gave us the model y equals negative 9.9785 times 10 to the negative fifth x, that was our slope, and then our y-intercept was plus 13.9508. And yes, I'm carrying a lot of decimal places to try to be as accurate as possible. Okay, so now let's take a look at how this model looks on the calculator compared to the data set. So if we go back to our calculator and we just hit graph, it adds in the linear regression line. Okay, so that's not bad. That fits the data pretty well. But let's see if we can do better with a different regression model besides linear. So we're just going to repeat this process, but we're going to look at other ones. So let's look at quadratic next. So again, we're going to go stat. We're going to arrow over to calculate, and then down to number 5, which is quadratic, and hit enter. Same questions, okay? List 1, list 2, yep. Where do we want to store this one? Let's store this one in Y2. So again, you hit your alpha trace, or alpha F4, and now we'll arrow down and tell it to store it in Y2. All right, and then we're going to ask it to calculate. And there's the model that it has provided for us, ax squared plus bx plus c. So then it gave us the coefficients for a, b, and c. And let's take a look at how it looks. Oh, okay. So there's the red line, there's the quadratic, and that looks pretty good. So let's go and let's write that model down, okay? So on our papers, our model for for quadratic regression was y equals 5.581 times 10 to the negative 10th x squared minus 1.34298 times 10 to the negative 4th x plus a y-intercept of 14.2601. Okay, there's our quadratic. And then the next one that we would look at would be cubic regression. All right, so back to the calculator. We're going to go stat, arrow over to calculate, down to number 6, which is cubic. Whoops, too far. Cubic regression. Hit enter. Arrow down to where we want to store it. We want to put this one in Y3. So let's take a look at, let's see, alpha F4. We'll arrow down to Y3, hit enter. and then we will calculate. Oh, it doesn't work, right? It says domain error. Value entered is not allowed in the function or command. Okay, now it gives you a whole bunch of gibberish, but basically what this means is, and I hope that when you look at the graph here, it kind of makes sense to you. This probably isn't, cubic is probably not a good fit, right? This data doesn't really appear to be snake-shaped at all. So on our papers here, we are just going to write error. Not a good fit, okay? And then incidentally, if you try to do Quadratic regression on this, you will get the same error message. And again, all you need to worry about is it just means that based on the data that you fed into the calculator, they're saying this regression model really doesn't work. Okay, so they're not even going to give you a model. But the one that we haven't looked at that we talked about that might work is exponential regression. So let's take a look at exponential regression before we make our choice on which one we like the best. So we'll do one more model here. Stat, arrow over to calculate, exponentials down here. It's number 10, it looks like, or number 0, I should say. So exponential regression, hit enter. And then we'll store this one in Y3, since technically we haven't used that one yet. So alpha, we'll go down to Y3. There we go. And calculate. And it definitely gave us one for this because, as we said, that really looked like it could be represented by exponential decay. All right, so let's write down our model real quick here on our paper. Our exponential regression is y equals 14.2108 times 0.99999 to the x power. Okay, that was the exponential model that they gave us. All right, so now we go back and we look at the graph again. Let's see how that exponential model fits in. Okay, and now you're probably thinking, this is getting a little messy. Like, I can't really see very well which model I like because they're all so close to each other and all lying on top of each other. So if we go to y equals, we can turn the plots off if we don't want to look at them. So for example, let's say we just want to look at the fit of the exponential. So if we turn this one off, if we go to where the equal sign is and we hit enter, it turns it off. And we can do the same thing here, just hit enter. Now the only graph that we should see should be our dots that we plotted from our table and then our exponential curve. So let's take a look at the graph. Wow, that's a very nice fit, I think. That looks really good. Okay, now I don't know if that's the best. So we can do the same thing. Let's look at just the quadratic. So I'm going to turn off y2 and I'm going to turn on, or sorry, turn off y3 and turn on y2. Let's take a look at that one. That one's pretty good too. Goodness. And then again, if we just wanted to look at that linear one again, and turn off the other two. Okay. I would say just on the shape of the data and the curvature of it that I would probably either go with the quadratic model or the exponential model. I wouldn't choose the linear model just because I think that the other two models do a better job of capturing the kind of the shape of the data as the values are decreasing. But I would say based on this information that with the data that we have, that all three models here look like they could be a good fit. Okay, so let's just make a little note. With the data we have, And those three models would be linear, quadratic, and exponential. Look like they could be a good fit. Okay. And as far as determining what the best fit is, well, sometimes you just have to go with your gut and say, I think the best fit is, quadratic, or I think the best fit is exponential. Sometimes it's very obvious which one is the best fit, but, if there's ever kind of a gray area, I would probably take multiple answers for the question based on the fact that there's a little bit of a gray area now, okay? So now we're kind of done with the calculator at this point, okay? Except for, doing some more calculations, but we're done with the regression models. You're going to be doing this multiple times as you practice the bookwork, but now we're actually going to go ahead and we're going to finish number 1 from page 82, okay? So kind of going back, letter A in the book for this problem asks us to make a scatter plot of the data. Okay, and then it asks if a linear model is appropriate, right? So on your paper, you can make a scatter plot of the data. And if you'd like to, you can actually use the graphing calculator to help you with this, because we already kind of have a picture here. If we just go to y equals and we turn off all 3 plots, whoops. Let me try that again. We turn off all 3 regression curves and we just look at that, we can kind of copy what that looks like. This doesn't have to be perfection here. It can just be approximate. Okay, our scatter plot looks something like that. And then, of course, we have our income down here, which is in thousands of dollars. And then up here we have our ulcer rate. Whoops. And this is per 100 people per population. Okay, so there's our scatter plot. And sorry, I forgot to go back to the screen. There's our scatter plot. I just kind of copied what I had there on the computer screen and labeled my axes. And it says, is a linear model appropriate? Well, that's kind of personal opinion, I guess. I think it could be. It could work. It's okay. It wasn't bad. I liked the exponential or the quadratic better, but that's my opinion. Okay, this is letter A. Then letter B says to find a linear model using your first and your last data points. Okay, so I'm going to sneak letter B over here on this page. Find a linear model. And this is using the first and last data points. So the first and the last data points from the data set were 4,000, 14.1, and 60,000, 8.2. Okay, so basically this is algebra 1. You have 2 ordered pairs. First you find slope, then you do point slope form to write your linear model. So my slope is going to be 14.1 minus 8.2 divided by 4,000 minus 60,000. And I grab my calculator and I get a slope of negative 1.05357 times 10 to the negative 4th. So a very tiny negative slope. And then I'm going to do my point slope form over here, which is y minus y1 equals m times x minus x1. So y minus 14.1 equals negative 1.05357 times 10 to the negative 4th times x minus 4,000. And of course, I distribute, I combine like terms, and I end up with a linear model of y equals negative 1.05357 times 10 to the negative fourth x, that's my variable x, plus 14.52 for my y-intercept. Okay, now they want us to compare this to what we got for our linear regression from part C. So, from part C, which we did already. We started with part C. So from part C, our linear regression was y equals negative 9.9785 times 10 to the negative fifth x plus 13.9508. Okay, so they wanted us to compare these two equations, and they're really close. 14.52, 13.95, almost 14 is a really close y-intercept, and those slopes are both very tiny negative numbers. So they are really quite close, all right? And then part D says, use the linear model from part C, so the linear regression model. That's going to be this model right here, right, that the calculator found for us. Part D says, use the linear model from part C to estimate the ulcer rate for an income of $25,000. So D, use the linear regression to estimate ulcer rate for an income of $25,000. Okay, now if we think about this, 25,000 lives within our set of data, right? Because our incomes in our data set go from 4,000 to 60,000. 25,000 is not a specific data point, but it does live within our data set. So remember, we would call this interpolating. Okay, so they're asking us to interpolate. Basically, when x equals 25,000, we get y is equal to negative 9.9785 times 10 to the negative fifth times 25,000 plus 13.9508. Again, you grab your calculator, you have your calculator do the math for you, and you end up with y equals 11.5%. Okay, which, if you look at where 25,000 would fall in your data set, it would fall between 20,000 and 30,000, where the ulcer rates are 12.4 and 10.5 respectively, and 11.5 is exactly halfway between those two values. So that fits our data set very well. All right, and then letter E is the last part here. Letter E says, according to the model, how likely is someone with an income of 80,000 to suffer from peptic ulcers? So this time they want us to use our linear, to use our linear regression model to estimate the ulcer rate for $80,000 incomes, okay, which $80,000 is outside of our data set because our biggest data value in our table was 60,000. So in this case, we are using our model to extrapolate or to find a value outside of the data set. All right, so we're just going to plug in 80,000 for x. So we got y equals negative 9.9785 times 10 to the negative fifth times 80,000 plus that y-intercept of 13.9508. You grab your calculator and plug that in, and you get y equals 5.97%. Okay, so that is how likely you have almost a 6% chance of developing an ulcer. Looking at the data, it should be smaller than the value at 60,000, which was 8.2, and it is. It's about 6%. So this does make sense. All right, so today in the set of notes, just a kind of quick recap, we've gone through the steps of using the graphing calculator to create different regression models for us so that we could pick the model that we felt best fit the data. But then the textbook wanted you to focus on the model for linear regression that the calculator produced to do some interpolating and some extrapolating within your data set.